Log on, tune in, find out. Another good idea from Cambridge.
No. It's a pleasure to have an Irish person here who will begin the lecture by telling us how to pronounce his name.
That's always a good way to start.
And after he's done that, he will tell us about the Fermionic T-duality. Thank you very much.
Yeah, very quickly. So you may be familiar with names like O'Connell, as in Donald O'Connell. This would be Donald O'Connell. Donald O'Connell was in the same undergrad class as me, so he works on scattering amplitudes. This here is Ov, but in the Irish language this would be O. It's basically an equivalent of Mach in Scottish. Scottish. And this name in English, because we use the Irish language as well, this is just John. So it's just a variant. And actually my name is, in English is John Paul. And in 1979, the Pope came to Ireland. So there's a whole lot of people of exactly the same age that are called John Paul. So to escape that, I changed my name over into the Irish language. And it's just Eoin. Okay, so.
Sorry, can I just start? It's a great place. I'm John Paul. To Fermionic T-duality. I can cope with pronouncing that.
Okay, actually, and it's funny because it moved me further back in the pecking order. C places you at the front. So I'd get in front of Gauntlet, for example. But Colgain places me behind. So yeah, the outline, what I hope to discuss is some work from last year with Ilya Bakhmatov, who's a PhD student of David Berman, and Hussein Yabartanu, who's based at Kyunghee University in Seoul. And this is what I was at Kies, and hopefully something that I will write up pretty soon. So I'm trying to understand this fermionic T-duality and self-duality in the supergravity. And most of the motivation for this comes from studying at least studies of scattering amplitudes in n=4 super Yang mills, and in one dimension lower in ABJM. And what people have noticed is that there's various symmetries: dual superconformal symmetry, Wilson loop scattering amplitude symmetry. And in 2008, Berkovits and Maldacena gave us a very nice geometric interpretation of this. So they came up with fermionic T-duality and a means to map AdS5 times S5 back to itself. Okay. These rules can be derived. The rules, basically how they derived these rules was basically looking at the sigma model, a Green-Schwarz sigma model, with, so you've got bosons and fermions, and you have some fermionic isometry direction. You gauge this fermionic isometry direction, and then you integrate out the gauge fields, you get the dual sigma model, and it's like the Boucher rules. You can read off what the transformation should be. You can also understand this in a very beautiful paper by Malcolm and Hadi, Malcolm Perry and, I don't know, his...
Hadi
Gadazgar, which is one of you two gentlemen, is it? Okay, it's an absolutely beautiful paper. It's a tremendous amount of work, and it's your first paper, is it? It's a fabulous paper. This is a paper from 2010, and they rederive these fermionic T-duality rules from just looking at the Killing spinor equations, and it's very nice. So I will discuss this briefly. Then what got me interested in this area about 6 months ago was that although AdS5S5 is self-dual, and we have this nice tie-in with these symmetries in the scattering amplitude, here we have lots of evidence that these scattering amplitudes have similar symmetries. And so, I mean, Simon Lee has been working on this with collaborators based in Korea, and also, I guess, Arthur Lipstein, Yuti Huang. Then there's an Italian group. Marco Bianchi is actually an office mate of mine at the moment, over in Oviedo, and he's been working on this as well. So they see very much similar kind of symmetries. But the problem is that what got me interested was that it's not understood how this is self-dual yet. So after a few years, well, it's been, 3 years at this stage, there's been various failed attempts, and you find in the transformation there's a singularity. So at some point this beautiful picture of Berkovits and Maldacena, it breaks down. So it'd be nice to understand what's going on here. And so last summer I decided to do some sort of study based on the PP wave limit of ADS4 times CP3. And there was previous work by David and Ilya where they'd shown that the PP wave of the maximum of this ADS5 times S5, the maximally SUSY PP wave in type 2b, that it's self-dual under 8 fermionic T-dualities. So I had a question mark about what happens when I take the PP wave limit of this. And then since then I've been kind of just studying, because everything simplifies in the PP wave limit, I've been trying to understand what exactly is going on when you have ADS spacetimes. So in particular the near horizon of this, ADS3 times S3 times Calabi-Yau. Okay. And I'm going to basically use some representation of the gamma matrices where gamma 0 is, well, in 16 dimensions, I can just basically bring 32-dimensional spinors or gamma matrices down to 16-dimensional ones. So my gamma 0 is just proportional to the identity, and then I have some gamma I. So all the formulae I'll write down are just in, they're 16 by 16 dimensional matrices. Okay, so how does this fermionic T-duality work? Or so if I write down Poincare in ADS5, and it doesn't make a difference whether or not I write or below. Let me separate this out. Right, or below the line or above the line. There's an inversion here. I can send or to 1 over or, and I still have Poincare. And so what Berkovits and Maldacena realized is that I can also do T-dualities. So the Boucher rules basically invert. If you do a T-duality on the GTT component, it inverts the metric. Okay. So what they proposed was to do. Let's see, there's dx2 squared in here. Is to do 4 T-dualities along ADS5, and in the process, your metric will become something like this, and you can cure this by doing an inversion. So you can bring it back to its original form. But when you do these T-dualities, these bosonic T-dualities, you also have a shift in the dilaton. So you end up with some transformed dilaton, and it picks up a factor like this. There may be a slight sign problem here.
Excuse me, can you remind me why it makes sense to do that T-dual things even without compactification?
I mean, I don't think at the level of
T-duality.
It doesn't really care. I mean, it's just provided you have an isometry direction, a killing direction, you can always do a T-duality.
But the real T-duality is only happening after you do the circle compactification. The physical contents, I guess, it should be somewhat.
I mean, there's lots of strange T-dualities that you can do. You can do, I mean, if you take ds squared. I mean, if you take polar coordinates, you can also do a T-duality here and end up with a singularity in the theta direction. I mean, there's lots of strange things you can do. I mean, you don't particularly have to worry about.
I mean, perhaps we say, I mean, you're using it as a solution generating symmetry, not necessarily at this stage.
Oh, so it's only a classical thing that you can do. There's no quantum exchange or.
So indeed, one of the things that Eoin, I'm sure, will mention is the fact that this thing is not exact to all orders in G string, but it's only true at tree level.
I see.
And so that's part of the equivalency.
I see. Okay.
So there's something called non-abelian T-duality that I've also been working on, and there's similarities between this and fermionic T-duality in some sense.
So how by inversion of metric you get this R squared in front of DT squared?
What do you mean?
I'm just stupid. I don't see how.
I'm just using T-duality rules, and
He's going to do T-duality in the time-like direction.
I'm doing T-duality on the
there
time.
is, the metric there is 1.
Sorry,
So
R
it's
squared.
OR, so...
Wait, no, maybe my handwriting is very bad. This is R squared downstairs. Maybe I should.
Okay.
Okay, sorry, I'm being very deep. So phi tilde is this, but what also happens is you start off with a phi form flux, which in this case is dt x1 dx2, etc. d or over or to the phi, and the self-dual part. Because you've got a phi form in type 2b. And when you do the T-dualities in the Ramond sector, you're going to end up dropping these indices. And you end up with something that looks like, sorry, this is OR. So your phi form flux becomes a one form flux, and it picks up an I factor, because when you do a time-like T-duality, all your Ramond fluxes pick up an I factor. Okay, so just to recap, you've started off with Poincare, you've done 4 bosonic T-dualities, you've recovered Poincare up to an inversion, but your dilaton has gone wandering, and your phi form flux has now become a one form flux, and it's also become complex. Okay. Oh, these are.
Sorry, I just missed the last part. Why is it complex?
Oh, it's complex because of this work from Chris Hall from 1998.
Oh, because of the timeline.
Yeah, it's a time-like T-duality. I mean, the Never-Schwarz sector doesn't change. It's the usual Boucher rules, but you pick up some I factor in Ramond fluxes if you do a time-like T-duality. Okay. So so then the task now is to use this Fermionic T-duality to bring the geometry back. And instead of just writing down the rules, what I'm going to do is explain what Malcolm and Hadi did, which was very nice, is that they constructed an ansatz. So they started off, and this is done in type, it's a tremendous amount of work, and quite instructive. They did both type 2b and type 2a. They wrote down an ansatz for the shift in the dilaton, because you want to counteract this shift here, and then an ansatz for the fluxes, how the fluxes would shift. So they have something like factor, define FA plus A, J, M, with potentially some extra terms in here, that I should explain. And in a similar relationship this is for type 2b. So we have a one form flux, we have a 3 form flux, and a 5 form flux. So they construct a shift in the dilaton. There's some scalar here to be determined. And then by ansatz, they introduce 2 killing spinners, okay, with no relationship between them. They introduce a matrix Mij, and they shift, incorporating this the dilaton as well. They basically shift, redefine the fields, if you like, with these bilinears. Then they pump these into the equations of motion, the new fields into the equations of motion, and make sure they satisfy the supergravity equations of motion using the killing spinner equations. So for example, this one here, to make sure that this satisfies the Bianchi, what we can, sorry, phi tilde, just phi plus x, we can multiply across here. We'll cancel the phi, we'll pick up a factor of e to the minus I x, fa. We know that the fa term satisfies the Bianchi. And then you basically develop some differential conditions between this scalar and the bilinear. Yeah.
Again, just because I don't know anything about this, does it act between type 2b and type 2b?
No. So again, yeah, sorry, it doesn't change chirality.
Theory.
It doesn't change chirality.
So it's one part.
Yeah, but non-abelian T-duality also does not change chirality, depending on the generator, depending on the dimension of the generator of the isometry group. So in some sense, it's a little similar to that. So what's nice is they're basically able to rederive, they find some relationships between this x and the bilinear and and this matrix Mij. So this could, instead of going through the sigma model and some pure spinor formalism, you can basically rederive all of these through some ansatz and stick it into the Killing spinor equation. So you can do this purely from the supergravity.
So here, I asked you yesterday. So it's a modified dilaton e to the, so which is given by scale root to g times e to the minus 2 pi. Is it invariant under this transformism?
It's e to the minus 2 pi times. No. I mean, this doesn't change. Your space-time doesn't change. So all that. Okay. So let me just write down what these rules are.
I think he's asking that you can write down a T-duality invariant dilaton.
Yeah.
But the point there is when you shift the dilaton and the fermionic T-duality, I mean, from the sigma model point of view, it's a bit clearer. The power of det G goes the other way. And that's because basically if you think of why you get a dilaton shift under T-duality, it's because of the measure, right? Only now you're integrating in Grassmann variables, and so your determinant will be the other way. And so when you get the T-duality shift for fermions, under fermionic T-duality, it goes the opposite way of the bosonic one.
So this is coming back to the
Power of the
this point here. So you have to get something that gives you the opposite sign here to shift this back.
So it shifts the other way.
Then this is, but also it doesn't change the chirality. So this is, I mean, this is all bundled together.
The second blackboard looks like some kind of field redefinition. I don't even understand why you call it duality.
Okay, we can, I mean, there's lots of things called, I mean, really, why this is called Fermionic T-duality is you can derive it from the sigma model. And you basically, if given some isometry direction, fermionic isometry direction, you're just doing a redefinition as you would in the usual Boucher rules. So that's why it's called Fermionic T-duality. That's why non-abelian T-duality is called non-abelian T-duality. I mean, because all of these things can be derived
The
from...
rules relate two very different backgrounds and identify
No, I mean, I agree with your point. I mean,
CFTs. Well,
you have an issue with this term T-duality, yeah? I mean, the similarity is at the level of the sigma model. Okay. Yeah, okay. So let me just write down what these rules are. So in type 2 supergravity, in d equals 10, we have your Killing spinor. Oh. Because the transformation is acting on the Killing spinors, and probably one small point I should mention here about Hattie's paper is this ansatz is nice is that they don't assume that these Killing spinors are related. So they have effectively a one spinor generalization of the work of Maldacen and Berkovits. And once e to j is proportional to epsilon I, they recovered the rules there. So in type 2 supergravity in 10 dimensions, you have two Killing spinors. Well, they're two chiral Killing spinors. And the chirality here depends on whether you're in type 2A or type 2B. So for type 2B, these have the same sign, and for type 2A, they have the opposite sign. Okay, so we're talking about Killing spinors. So basically, you have to start with some background that preserves supersymmetry, and then. Okay. Let me, we'll write this somewhere else. Let me just explain what these things are. So the whole transformation comes down to determining some auxiliary matrix Cij. So this is this Mij here. So all I've done is rewritten the rules the way that Maldacen and Berkovits presented them after they had done the conversion to type 2 supergravity. So you have these two Killing spinors, these Majorana wild, well, they're wild Killing spinors, and you have to construct some matrix C from this bilinear here. Okay, and it has to, this I runs over the number of fermionic T-dualities that you want to do. So the simplest case is you just have I is equal to 1, and this matrix is just it's just a function. So here you have some constraint condition, and Malacina and Berkovitz sort of said this came from demanding that your fermionic isometry was an abelian isometry. But what's nice about this is we can see this condition in the language of Malcolm and Hadi as basically an integrability condition. So if you act on this condition, if you act on this differential condition again with the Killing-Spinner equation, you get something that's proportional to some bilinear wedged, contracted into H, some field. And you can see, well, you get this bilinear contracted into H. So in some sense, this is instructive as well. You can see where this condition comes out. And then you're shifting your dilaton, it's just given by the trace of the log of C. And then there's a rule for the unified tilde F tilde alpha beta I 16. Okay, so then finally there's some bispinner that's basically some sum of your fluxes that transforms in this way here. So in David's paper with Ilya from 2009, there's a tremendous calculation done where they do one fermionic T-duality. So when you do one fermionic T-duality, you end up with a horrendously sparse matrix here. This means to counteract the shift, you have to turn on a large number of fluxes. So what was done in that paper was basically to do one fermionic T-duality. I forget if it was D1 or the PP wave, but then basically to write down some zoo of fluxes and check that they satisfy the equations of motion. And so it's very nice. And this, okay. I mean, this is just the usual thing that you would expect. Some one form, gamma mu nu rho, alpha beta with some factors, f mu nu rho, 3, etc. Gamma mu nu rho. 5 form. Okay, so that's what that thing is. And depending on, so when you do these transformations, you end up with a bispinner. So you construct a bispinner, you end up with a bispinner. Then you need to read off what the constituent fluxes are, and typically that boils down to looking at the symmetries of your gamma matrices. So if this thing is either symmetric or antisymmetric, well, so typically these things are symmetric, or at least in the conventions I've been using. So the 5 form and the 1 form come together, and then the 3 form is antisymmetric. So you basically just have to decompose this matrix into symmetric and antisymmetric parts.
Does your F1, F3, F5 include B field in the
Yes.
definition?
Yes.
And you can write down
They're
the
gauge invariant, yeah.
transformation of the gauge field itself. You can read off.
Yeah, I mean, I have a nice example that where it actually it turns out that way, that these incorporate these things. Okay.
And the B field's invariant.
Yeah, the B field doesn't change. So these are the only things that
Those
change.
field strengths are the field strengths which include the B field.
Yeah. Yeah, so the B field just is a kind of a spectator in the background, as is the metric. The space-time doesn't go anywhere. Okay, so yeah, so when you perform this fermionic T-duality in ADS5 times S5, what you then notice is that this factor here, this came with +4 natural log of Bohr, you get the -4 natural log of Bohr, and you also find that your fluxes, that this Cij will have it's symmetric for ADS5 times S5. It has a 1 form part and a 5 form part, and the 1 form part cancels this part here, bringing you back to the self-dual 5 form. And that's how it works out. And it's important that you haven't, that these things, this equation, well, okay, it's important. Okay. What's important here, and I probably didn't stress it, is that these are complex killing spinners. So there's a slight, if you work in Majorana Y representation, your killing spinner should be real. And in this representation, this gamma 0 is just proportional to the identity. So you have these real Killing spinors that satisfy this condition. You can't, I mean, you can't satisfy this unless you complexify the Killing spinors. And as a result of this complexification, you will end up with complex fluxes. So this is not a way to generate new solutions, unless you're interested in solutions with imaginary fluxes.
Or you just do it many times.
Yes, as we will see in the PT wave case. And this is another nice thing about David's paper from 2009. It's a very, yeah, no, I think it's a very instructive paper.
I'd like to rephrase my question. Is it possible to derive the transformation rule for the gauge field, not field strength, in a non-local way? Probably one should get some integral formula. Is it possible to derive the transformation rule of the C field and the gauge field itself?
I don't know. I mean, David?
Oh gosh. Well, I mean, you got a relation of the field strengths, right? Gosh. So that implies the transformation of the potentials up to gauge fixing. Now.
No, in a non-local way, whether.
But it's not. I mean, but it's not done beyond that. I mean, you're just given the relation with the fluxes.
Okay.
There's no direct. I know what you're thinking because in the bosonic thing you do it with potentials. In the Fermionic T-duality, it's the fluxes.
Okay, so there's a nice paper by Ilya from. I think it's 2010, so it's the end of 2010, and it's done in the supergravity where he looks at ADS4 times CP3, and what I like about Ilya's paper is I can understand it because it's just in terms of Killing spinors, and there's also work by Yaron Oz and collaborators, so Ido Adam and I think Deco is the other co-author, where they basically try to show that this space-time is self-dual. I mean, here things work slightly differently. You only have ADS4 and it's not ADS5. So if you want to do the T-dualities, you have 3 T-dualities. And if you do 3 T-dualities...
I was just perhaps make a comment of the point of the self-duality is that although everything's invariant in space, you get back to ADS5 plus S5, because you've done the T-duality, the bosonic T-dualities, on the boundary of the space, you've changed from Dirichlet to normal boundary conditions and vice versa. So any ADS calculation of something like a scattering amplitude would go over to a Wilson loop. So the origin of, I mean, I'm just saying that it's key to motivate why you'd care that this thing is self-dual. I mean, you know, normally you get a whole bunch of dualities and get back to the beginning. Why would you bother, right? It's because on the boundary you've changed the boundary conditions still, but left the bulk invariant. So that's the origin of scattering Wilson loop duality.
Okay, thank you. No, it's good. I mean, I mean, apart from a handful of people working in this area, then, well, yeah, I mean, it's not a very large community.
So that was the question with ADS4, whether there's a Wilson loop scattering amplitude duality in that case.
Yeah, but there seems to be, I guess there are papers written on this, so there seems to be some...
Are we coupling what's known?
Pardon?
Are we coupling what's known?
Weak coupling for the EBJM scattering, or we had a talk by Sanjin.
I haven't done the computation, but from the papers I read, I see up to 6.2 loops. Things are working.
So as far as anybody has computed it, it works. Okay, so you expect it should.
And there are even some speculation that it'll go through all loops like a PDS type conditions.
Yeah, so the mini symmetry seemed to be there.
When we started this, I thought it would be true, but then, it seemed to be more complicated, which is what's going to be.
Yeah, so I mean, there's basically 2 papers here, and there's this paper here. So there's various people have tried it. I mean, what I wanted to say was that here you only have 3 T-duality directions, and when you do 3 T-dualities, you go from type 2A to type 2B. So clearly this doesn't work. So you have to introduce 3 more T-dualities, and these are T-dualities along the CP3. and then you need to compensate with some fermionic T-dualities. And there's a nice paper by, I think it's Bart here, et al., where they studied the superconformal algebra, and Carlo Meneghelli was one of the co-authors there. And this is the recipe that they've come up with. I mean, and it seems reasonable. I mean, we do 6 and we get back to type 2a, and then we just have to compensate. And what I should say is that although Maldacen and Berkovitz you do 4 bosonic plus 8 fermionic, there is an alternative description where you do 4 plus 4 plus 8, and the 4 are isometry directions along the S5. And you basically have to complexify the S5 and choose complex killing directions on the S5. I will get to that because I understand how that works now completely in ADS3 times S3. So it's so what is interesting is that Ilya did this calculation. I mean, there's no problem with these shift. Well, actually, what Ilya just did is Ilya looked at the dilaton. So for it to have any chance to be self-dual, we need a shift in the dilaton going one way, and we need a shift in the dilaton going the other way. So he didn't worry about the fluxes. The geometry is more complicated. And he finds a plus 3 natural log of 4. Then he complexifies CP3 in a certain way, which I may not write down. And he finds, he basically does 3 bosonic T-dualities, and he finds a singularity in the dilaton shift there. And then when you do those 3 bosonic T-dualities, you want to find fermionic isometry directions that commute with the bosonic directions. So Ilya basically solved this equation here. So he looked at the Lie derivative of the killing spinors with respect to the isometry directions on the CP3, and this basically gives you a projection condition. So from your killing spinors, it picks out certain killing spinors to construct the fermionic isometry directions in. Now the thing is, nothing here works out. So, I mean, apart from the shift from the ADS4 directions, there is a singularity here, and not surprisingly, this also gives you a singularity. So the feeling is if you can identify the correct, well, maybe there's an obstacle, but if you can identify the correct isometries here, then there shouldn't be, well, it would be nice to see if you could avoid these singularities.
I mean, perhaps you could phrase it one way. You get a 0 and you get an infinity.
Yeah.
I mean, in the sense that you could write to the dilaton should go back to itself, but what you get, I mean, completely stupid way of putting it, is basically infinity divided by, well, 0 divided by 0,
right?
Effectively. Right? So you get, so then it's whether you believe that 0 divided by 0 is sensibly 1. But of course that doesn't make any sense.
But he still hasn't looked at the fluxes.
Yeah.
So, I mean, there's a big question about whether this thing is, how it works, and whether it's
I mean, the point is that they're sort of uncontrolled singularities. So but they come in ratios and both blow up. So it's not, doesn't mean it doesn't work, it just means that you've not controlled the singularity.
Yeah. But it's okay. But I mean, it'd be nice to recover under some transformations to recover the geometry. And I guess this is the goal of the exercise. So I was very excited that people had been working on this for a while and it wasn't clear why this worked. So I thought something very simple that I could do, and I was very excited about this, was that I could look at the PP wave. Because of David's paper on the PP wave limit of ADS5 times S5, we knew this was self-dual just under 8 fermionic T-dualities. Now there's a reason why you don't, I mean, when you take the PP wave limit, you don't have any radial direction for ADS. The geometry completely simplifies, and you just basically, if it's going to be self-dual, it just has to be self-dual with respect to fermionic T-dualities. So what you can do is you can take ADS4 times CP3, and you take its PP wave limit, and the geometry looks a bit like this, dx plus dx minus some function of xi, dx plus squared. Squared in transverse directions, and then mu f plus 4/3. And then a of xi has to take some special form for it to be u squared over 9 xi squared plus I equals 5 over 5 is 8, u squared over 36. Okay, so this is what the pp wave limit of ADS4 times CP3 looks like. So you've got two types of fluxes. You've got a 2-form, and you've also got a 4-form flux, so it's a little different from the maximally supersymmetric case where you just have 5 forms. And you have this this function a, depends on the transverse coordinates xi, and it looks something like this. And I mean, so the only scale that's really entering is this constant mu. Okay, so you can work out what the killing spinors are for that. And this background has 24 supersymmetries. See where I can go. I want to keep these. If I can. Go. So move that up a bit. So you can work out what the killing spinors are. U over 6, some I x plus, epsilon plus plus. Epsilon plus minus. I mean, so this is horrendous notation, and it's, I mean, okay. Gamma plus actually on epsilon plus just means, so these means that the epsilon with these superscripts just mean it's in the kernel of gamma plus, and this one's minus. And then the plus below is a projection condition under the one projector that turns up, so it's plus minus and plus minus. So it's a little bit more complicated than the pp wave limit of the maximally supersymmetric case. I haven't defined what I is. It's gamma 1, 2, 3. It's not important. But what you see here is that there's two types of killing spinors in the pp wave limit. There's ones that depend on the x plus coordinate, this one and this one, and then there's one that depends not on x plus but depends on the transverse directions. And this is usually how they always split up. And typically the supernumeracy killing spinors, the ones, typically a pp wave has 16 supersymmetries, irrespective of what the form of A is. It can be any function you like. You will always have 16 supersymmetries. These are basically those 16, and then there's an extra 8. So something special has to happen in the solution for you to get extra supersymmetries. But what you can do is you can, so from these killing spinors here, you can construct fermionic isometry directions. And from the 16 that you have, there's 8 fermionic directions that you can produce. You calculate what this Cij is, and you work out what this thing here is. And what's interesting is that this is proportional to this here. So this matrix is just some multiple up. It's a constant times this matrix here. So this tells you that the overall fluxes are just scaling by a factor. And this factor is basically just proportional to the one scale that you have, which is mu. And what was interesting about this was that for each case, we did study a couple of different cases. We started off with the pp wave limit of A to Jm. There's a superposition pp wave limit that's basically if you take two A to Jm pp waves, you have 20 supercharges. And then the generic case where this A is not, there's nothing special about this, you have 16. So in all these cases, we get exactly the same formula, which is 8 Cij inverse epsilon I alpha cross epsilon j beta hat is equal to I e to the phi f alpha beta. So basically this thing is proportional to this thing here. by this, and as a result, your fluxes just scale in a certain way. I haven't written it down, but all your fluxes go like basically mu to the -1, and your dilaton goes in the opposite way, effectively. So this is the effect of the whole thing. Your dilaton also, it just shifts by, I mean, you started off there was no dilaton, it just becomes a constant, which is this mu. And what's nice is that if you look at the equations of motion, the equation of motion for PP waves, or in general, is just you have some curvature term. For type 2a and type 2b, you have terms like this. Mu squared minus mu. So the only thing that changes is that the dilaton scales in one way and the flux scales in the opposite direction, and the overall thing is exactly the same. And so this is what David noticed as well. More or less this relationship is what David noticed in type 2b. So we've got 4 examples. The thing is, I wanted to go further. I wanted to take the most general PP wave, but there's no very good classification of PP waves. There's a lot of work on it, but there's no completely general classification. But there seems to be something there, that we were getting this formula all the time suggested there's something there. And so under this fermionic T-duality, if you do 8 fermionic T-dualities, you can bring the PP wave back to itself, up to a constant shift in the dilaton, and a rescaling of the fluxes. Okay? Yeah. And yeah. So you haven't, what was it, I was wondering before I started whether or not I would see any signature of the reduction in supersymmetry. So here we have 32 supercharges. Here we have 24. So I was wondering would I see 6 fermionic T-dualities, but you don't see that. And the reason is because you're always using the fact that there's 16 supercharges in the PP wave. Okay. So you don't learn anything about ADS4 times CP3, but what you can show is that its PP wave limit is self-dual. But it looks like this is a relatively trivial redefinition in the matrix model. So you're just redefining things. It's pretty trivial. Okay. And what I should say is that David and Ilya did in their paper is that there's 8 fermionic T-dualities, 8 commuting directions. They looked at what happens if I do 1 fermionic T-duality, what happens if I do 2 and I do 4 and then do 8. And I think it was 8 was the only case that you got a real background back. And maybe with some of them you got maybe an I factor in the fluxes or the dilaton or...
Yeah, it looks like you need to do some multiples of 8.
Yeah. And so yeah.
To get real solutions.
Mm-hmm. Okay, so I've got about 15 minutes left. And so, I mean, this is very trivial. I had a chat with Sujong Ray about this, and we looked, and we started looking at the matrix model, and it seems like it's a very trivial sort of thing. So, a good place to, well, at least try to understand what Berkovits and Maldacena have done for ADS5 times S5 is to do the D1, D5 near horizon. And here we can have T4 and we can also have K3. I mean, it's more or less the same as before. But here because you have less supersymmetry again, you have 16 supercharges. Instead of, let me remind you, for ADS5 times S5, it's 4 bosonic and 8 fermionic. Here you expect 2 plus 4. And where it was 4 plus 4 plus 8, and these are the 4 bosonic on the S5, it becomes 2 plus 2 plus 4, yeah. Okay, and then I also had a small question about S-duality and whether S-duality commutes with fermionic T-duality. And I also wanted to see if I could push this as far as K3. It's difficult to explicitly construct the killing spinners when you have K3. They become covariantly constant rather than just being constant. Yeah, and this case here was done explicitly by Maldacen and Berkowitz. So they work out what the killing spinors are, they work out what the Cij is, and they show how it all works. This case here is, they just basically, they don't explicitly go through it. So I had a slight question mark about how this thing works.
Was that in the Berkowitz-Maldacen paper?
Which one?
The 4 plus 8.
Yeah, that was, they basically, looking at the superconformal algebra, they argued that this would work. And they say it does work. And what's, the thing that you have to do is that you have to take the S squared S5 and you have to complexify it and change it into de Sitter in some complexification. So here we've got 4 translation directions. So this picks out your 4 directions from the 5-sphere in the complexification. So, okay. So yeah, let me. Okay. Yeah, I mean, it's, okay, I mean, so here, it's pretty straightforward procedure. You want to calculate the killing spinors for this background, and then you want to determine what this Cij is. You determine what the Cij is, and you find that the Cij just depends on the radial direction. It depends on theta, phi, and psi. So it's basically, okay, there's a good reason for this. So it depends on this radial direction here, and then theta, phi, psi. And the reason being is because typically when you do these fermionic T-dualities, you pick out the Poincare supercharges. Now, Poincare, if we can consider the killing spinors on ADS, they look something like or to the minus a half times epsilon 0, plus there's some or to the half, I forget, x of x, I forget what's here. But I mean, the point is that the Poincare ones just depend on the radial direction, and the superconformal ones depend on the coordinates, the time direction, and x1, x2, x3. So these are the far more complicated ones to use. So you introduce a projection condition here, and this projection condition more or less kills the dependence on the 0, 1 directions. Introducing this Poincare condition. It also, at least for this case here, this Poincare condition, I'm probably not going to use, it looks something like this, and it basically means that epsilon hat, you had 2 Majorana-Weyl spinors in type 2b, that they're actually not independent. Because of this Poincare condition, they get related, so you just have 1. And you just have to figure out what goes on there. Okay. So let me just yes, okay, one thing that confused me here was that I was expecting it to be to get self-duality. Okay, so I was expecting this 2 plus 4 recipe to work out, but if you do 4 fermionic T-dualities, so you start off, you satisfy this condition, you do 4 fermionic T-dualities, you find out that this guy is antisymmetric. So this means, oh, I'm running away. Okay. To complete the geometry, the geometry to start off with has a 3-form flux. Okay. Now, if you do 2 bosonic T-dualities on the ADS3 part, you'll get a 1-form. And 2 bosonic T-dualities here will convert this into a 5-form. So this should tell me, if I expected 2 plus 4 to work out, I would expect that my fermionic T-duality is going to take my 3-form flux and turn it into a 1 and a 5-form flux, but it doesn't do that. What it does is it makes this thing antisymmetric. So it takes a 3-form and turns it into a 3-form. And the 3-form that you get is basically some complex your wedge J, where J is basically the Kähler form on the T4. Okay, so then you can try and do, so this is the result of your fermionic T-duality. You do your two bosonic T-dualities on that, and you get to some F5, which is basically the ball of ADS3 with some, okay, we've dropped the I factor, wedge J. So you started off with something that had a 3-form flux, and it's the near horizon of D1, D5. It's ADS3, S3 times T4. You do the 2 plus 4, but instead of getting back to geometry, you do get back to geometry. Geometry hasn't changed. The fluxes have gone to be 5-form fluxes. So you start off with D1, D5, and you end up with D3, D3. Now that's not a problem because you have T4 and you can do the T-dualities here. And so you can bring this is self-dual and the self-dual part. So when you do the T-dualities here, you get back this. Okay, and you move over here. So what I wanted to understand, actually before even getting to this other point, I had a small question about what happens if I replace this 3-form flux with a B field. So in type 2b supergravity, this geometry can be supported by either a Ramond-Ramond 2 form or a B field. And if you replace with a B field and you try to repeat, what you find is you encounter a singularity. So basically this B field, its field strength H has to be proportional to the volume of ADS3, and then of course the volume of S3. But when you calculate what BTX is, it looks like 1 over R squared in a particular gauge. And when you go to do the Boucher rules, see what's this? Yeah. If you try to do a T-duality on the time direction, with a B field mixes the X direction with the time direction. This X direction is this spatial direction in AS3. It mixes them, and as a result, your GXX term in the metric, it also changes. And so what you find here is that they started off as 1 over R squared, and let's see. Yeah. However the signs go, this becomes R squared upstairs, and you get 1 over R to the 4. So this gives you a 0. So if you try to replace this 3-form flux with a B field, which will still support the geometry, you run into a problem with the bosonic T-duality. And it gets worse than that. Your projection condition from Poincaré is very strong. It's so strong that it tells you that this has to be equal to 0. So if you try to do a fermionic T-duality, it becomes completely trivial. I mean, basically, this rotation of the killing spinners is just a constant. It doesn't depend anywhere on the space-time, this B field. So you can now go back and use the fact that there's a whole class of geometries. I can do an S-duality transformation.
Can I ask you a very nice question? So if you just go back to this thing, I mean, so you need H flux, right, to be turned on. And then what you've done when you say BXT is equal to that, you've gauge fixed.
It's a gauge choice, but it's a natural one.
Yeah, well, okay, fine, but is your but I'm worried that your result's not gauge independent. I mean, I need H. I mean, I need H to solve.
No, H appears in the fluxes.
Exactly, H appears in the fluxes.
In the fermionic.
And that's what you need for your ADS3.
No. I mean that if we consider the gauge invariant fluxes that will go into the flux by spinner.
Yeah, no. You just said instead of having. Instead of having.
Or whichever. That's
No, what you said was instead of having F3 to support the ADS3, you have H3.
Yeah.
So that's all you need in terms of supergravity.
Yeah.
And then you've done a gauge fixing to write down the potential so you can do bosonic T-duality. So what I'm saying to you is...
Well, okay, this comes straight from the Killing
No,
Center.
not the Poincaré. That right there, that bosonic thing.
This one here.
Yeah. The fact that B is equal to that, and then you do ordinary bosonic thing in terms of that potential.
Yeah.
Why could I not get a different potential for B?
You can add a constant.
No, I can do more than that.
Can you?
Yeah, because it's a three-form flux, right? So when I write down the potential for a constant three-form flux, and then I think you can do it a bit differently.
I mean, okay, you want your H3 to be... we can discuss this later.
dB, right? So, yeah.
You want it to be something like this, so...
Yeah. So, for example, I could have a BYT. It's a function of... I'm pretty sure that's not the only gauge.
Well, okay, let's discuss later, because the other thing is TST doesn't seem to help navigate the singularity.
No, that won't change it. That's invariant.
Okay, so written down somewhere. So I mean, what you can do is you can do there's a whole type 2b supergravity has SL2OR symmetry, which can also be referred to as, I guess, S-duality. You can basically turn on C2 and B at the same time. And if you turn on both at the same time, your dilaton is still just a constant, so you can set it to 0. The axion isn't affected. So it's basically just a rotation. So you still have the space-time, you just rotate. I mean, we introduce some angle, and these guys are rotated. And what you find is that your killing spinner, this is pretty well trodden stuff. Your killing spinner gets rotated. Your killing spinner gets rotated, and the effect of this is that the Cij that you had before picks up a factor of cos alpha, where basically C2 is proportional to cos alpha, and then this is proportional to sine alpha. And you can go through and you can calculate Cij. You can stick it in here. You can read off what the fluxes are again. Again, they're antisymmetric. You figure out what they are. You find that you find all these fluxes turned on, and some of them incorporate the B field. And when you basically do so we've done the 4 fermionic T-dualities. The matrix is more or less the same as before with this cos alpha. We do get, it does work out. It gives you a solution to the equations of motion, but what seems to be problematic is at the very end is that you end up with at the end of some work, you end up with a 3-form flux that's proportional to sine alpha, and it's imaginary, and a 5-form flux that's proportional to cos alpha, and it's real. There's other expressions here. So all it's telling you is that just by turning on a B field, your geometry that was self-dual before is no longer self-dual. So you've just done an S-duality transformation, and the only way to make it self-dual again is to get rid of this. Your fluxes have basically separated. And there's no way I can compensate. I mean, this is at the end of a time like T duality. This F3 has to go. And so if you set alpha to 0, then this F3 disappears.
In the point of view of the boundary theory, at least in the ADS5 case, the S-duality isn't going to preserve the plane limit.
So the S-duality S-duality is, for the 5-form flux, it's trivial. It doesn't do anything to that.
Wait, so in the ADS5 case?
So ADS5 is supported by a 5-form flux. And now if I do an S-duality transformation, nothing changes.
Well, the dilaton will.
The dilaton.
Dilaton will, let's see. Well, I guess it'll be a constant afterwards.
Yeah, but
I think what I'm saying is that the S-duality is not expected to be a symmetry of the plane limit of the boundary theory.
Okay.
I only expect the scattering amplitude Wilson loop duality at least to hold in the plane limit.
Okay. Yeah. I mean, there's reasons to believe, well, why the Fermionic T-duality wouldn't commute with S-duality. But here's an explicit...
I mean, you might be telling me there's something more general that represents a
It's an explicit calculation that shows that. And let me just finish off.
So 1 minute. So you say it doesn't commute.
Yes. Okay, so so here's a calculation that says it doesn't commute, although the calculation works out nicely. And the last thing is understanding what these internal bosonic T-dualities are. So there's a recipe where it's 2 plus 2 plus 4, and you have to figure out how do I do 2 bosonic T-dualities on S3. So you take your metric for S3, and you analytically continue, you complexify it, and you end up with a minus d omega squared, dx1 squared, plus dx2 squared, divided by omega squared. So this is some version of de Sitter. So you have 2 isometry directions, x1 and x2. Now there's something called the spinorial E derivative, which is defined to be some factors dk m n gamma m n epsilon. There's an epsilon. Okay, this thing here. So you have a killing direction. This is this km. It's contracted into the convariate derivative here. It acts on the spinner. And then you take the derivative of the killing direction and then contract it into some gamma matrices. And this is the spinorial E derivative. It has some very nice properties. But you basically, it tells you if your killing spinners are invariant under this isometry direction. So what you want to do is you want to take del x1 and del x2, and you want to pump them in, you want to put them into this expression here. You get exactly the same projection condition. Maybe I'm not being clear. So your killing spinner on this geometry will have an or to the minus a half part. This is the part that cancels the shift in the dilaton. But then it's got parts that depend on depends on the angular coordinates on the S3. So there's an e to the theta, e to the phi, e to the psi, and then there's a constant part. So this is complete radial dependence. You find that basically by imposing L of del x1 of epsilon equals 0, or L of del x2 epsilon equals 0, you get a projection condition that acts on epsilon 0. And this looks something like I gamma 4 5 epsilon 0 equals epsilon 0. So what it's doing is the projection condition. So it basically, it selects the killing spinners that you should use to do the fermionic T-duality. And once you do this fermionic T-duality, you can see that you get back what you, well, it's slightly in complex it's written in complex coordinates, but you find that everything works out. There is a slight difference here. With this 2 plus 2 plus 4 recipe, I basically get the geometry back on the nose. Whereas with this 2 plus 4, the geometry comes back, but your 3 forms get replaced by 5 forms. So it looks like it's a rotation. And yeah, I anticipate that this whole thing works for K3 as well. There's a good reason for that. This del mu it's written here. Del mu Cij is just this expression here. And if you put in this, well, let's call 6, 7, 8, 9, the directions along the Calabi-Yau or along the T4, there's no vector bilinears along the Calabi-Yau. So Cij doesn't depend on the Calabi-Yau. And because Cij generates your whole transformation, it shouldn't make a difference whether or not you have T4 in there or some orbifold or K3. So it looks like the D1, the near horizon of D1, D5 is super symmetric. Well, is self-dual. All right. Well, thank you for your time.
Any questions?
This rescaling of fluxes, is it consistent with a Dirac quantization condition?
Which rescaling of fluxes?
I mean, at some point you said that the 2 backgrounds were equivalent up to rescaling of fluxes. I was wondering if the
Oh, okay. No, you have different charges. So I mean, by the Dirac quantization condition, you mean some sort of charge quantization condition?
Yeah, so if initially you had a solution which satisfied all the charge quantization condition, is the final solution also guaranteed to satisfy charge quantization conditions?
That's something I don't know. I mean,
No.
it's
I mean, you'd have to impose it on top. But it's the same when you do ODD.
Yeah, okay, so that means
okay.
that this
Exactly
group,
analogous,
so
or
there's going to be some
SL2R,
discrete subgroup that survives.
Yeah, so you do it, and then you go, oh, I should land on a discrete lattice.
Okay. So is that lattice known or?
Well, I mean, it's going to be, I mean, you just got all the Riemann-Riemann fluxes, right?
Okay, so you have to.
So you just apply the direct quantization to those fluxes.
But yeah, I haven't thought about it. I mean, you could try and quantize. I mean, there's a general thing here. I mean, this geometry. I mean, with K3, there's yeah. I mean, so when I think of the D1, well, this geometry, I always think of D1, D5. So I think of three-form fluxes, and potentially a K3 in there. But I guess in the supergravity literature, it can turn up with K3. We're just being sourced by a 5-form flux, and then there's a question about how you go from one to the other with the K3, and this should be some mirror symmetry transformation. But yeah, I mean, maybe flux quantization is another concern on top of that as well.
I think it's just the same as with bosonic case. Or SL2R goes for SL2Z.
Mm-hmm. Okay. Yeah, so it's more
Anybody else? Okay, let's thank John Paul again.
thank you.